Well, I cannot believe we almost made it through our entire first semester of General Chemistry 1, almost ready for our final exam. I can almost guarantee there will be some of these questions that I'm about to review, just kind of random review questions based on stuff dissolved in water and stoichiometry thereof. So I better get going. I have quite a few slides. We'll see how many slides I get through. We'll see how much patience I have. See how much patience you have for watching these silly things. So I wrote a chemical equation to help explain in more detail what's going on here. If I had 100 milliliters of barium chloride solution and 100 milliliters of iron sulfate solution, one in each of two different beakers, and I think I've got something tricky going on here because they give me an amount of this chemical and an amount of this chemical. They're both dissolved in water, but the point is, how do I know which one is the right amount to use? And the answer is I don't until I carefully consider molarity times volume and molarity times volume to give. I like to use millimoles. If I have 100 milliliters times 1.1 molar, that's 10 millimoles. The milli survive the multiplication, milliliter and moles per liter. The liters cancel, and I have millimoles. So a millimole is 1/1000th of a mole. But the balanced equation says I need 3 times more barium chloride than I do of iron sulfate. That's, a 3 to 1. That's why the molecular equation is often handy if you're doing stoichiometry and titration and such. So it seems like I need more barium chloride, and I don't have it. I would like 30 millimoles, like maybe 300 milliliters or something. So if that's the limiting reactant, I would say 10 millimoles of barium chloride. It's a 3 to 3 ratio because the question up here says what mass of barium sulfate can be created. It's like I said, 3 to 3 ratio. And the molar mass of barium sulfate, 1 barium and 1 sulfur and 4 oxygens, adds up to 233-ish. Interesting. Another question. I've set these up so that you can theoretically pause them and try it yourself, or at some point try it yourself if you like. In any case, 100 milliliters of 0.2 molar potassium hydroxide, 100 milliliters of 0.2 molar aqueous magnesium sulfate. Almost all, a vast majority of our simple chemical reactions can be done in water, and aqueous gives the ions or molecules or whatever a chance to mingle. Again, they're giving us 20 millimoles of this one and 20 millimoles of this one, and asking the question, write a balanced chemical equation, what precipitate forms, what mass precipitate forms, find the concentration of each ion remaining in solution. I don't know if I'll do part D. I'll certainly do parts A, B, and C though. I think the chemical reaction would be something like KOH plus MgNO3 twice gives magnesium hydroxide solid, that forces the reaction. Potassium nitrate is still aqueous. So here I got lazy, aqueous. Potassium ion aqueous is a spectator, and the nitrate ion here, aqueous on both sides, is a spectator. And the net ionic would be magnesium 2 plus 2 OH minuses reacts to give magnesium hydroxide solid. Twice as many moles of KOH are needed, and I don't have those. I only have I have 100 milliliters times 0.2 molar, that's 20 millimoles of KOH and 20 millimoles of magnesium nitrate. So since I really need twice this number, I don't have it. I would like 40 millimoles of KOH to react with 20 millimoles of magnesium nitrate. I'll use that as a limiting reactant, and the limiting reactant determines how much product I get. So the moles of KOH, 2 moles of KOH to 1 mole of magnesium hydroxide, and then the molar mass of magnesium hydroxide. Change moles of magnesium hydroxide into grams. Oh, I left the millis over here, so the milli survived. But if I want to change my final answer to grams, I move the decimal here 3 places left. I'm going quickly with the knowledge that you can pause this and go back and look at the PDF perhaps as well. Write a balanced chemical equation for the net ionic reaction for the reaction that occurs when the constants of the two beakers are mixed. What colors represent spectator ions? Do you know your solubility rules? Isn't it true that most sulfides don't dissolve in water? So when this copper ion hits this sulfide ion, Cha-ching! A chemical reaction happens. Sound effects. Kidding. Not really, I'm just being stupid. But the sodium and the nitrate are spectators. The equation would look like this. Equations. The molecular equation is yeah, it's a 1-to-1 ratio because copper is a 2 plus, sulfate's a 2 minus, sodium's a 1 plus, sulfide's a 2 minus. But yeah, copper sulfide, 2 plus, 2 minus, canceling the two sodiums on each side. Hang on a second. I have an interruption. Always somebody banging at my door. That's good. Makes me feel wanted. Just kidding. Well, it does, but always glad to help good students with chemistry. Where was I? Oh yeah. Oh, don't look at the answer. Another one here. It says write a balanced formula and net ionic equation. I call those molecular equation and net ionic equation for this one. Solubility rules. What's going to react with what? So in the left-hand beaker I have cobalt chloride. On the right-hand beaker I have sodium hydroxide. This dissolves in water really well. This dissolves in water really well. Nothing happening until you pour the two together. In which case, the ions mix, and the question is: would this positive like to come together with this negative? Is there any driving force there? Or would this positive like to come together with this negative? Is there any driving force there? And the answer is, if you know your solubility rules, yes to the first question, where the cobalt 2 plus and the hydroxide. Most hydroxides don't dissolve in water. So when the cobalt ion hits the hydroxide ion in the other, when the cobalt ion in this water hits the hydroxide ion in this water, and there are so many millions and millions of them, they do collide and they come together in a form of insoluble little crystals of cobalt hydroxide. Cobalt's famous for having cool colors, so I'm pretty sure this would be I don't know, red, pink, purple, orange, something. It's been a long time since I've done that precipitation. Alright. Spectators are, you know what the spectators are, sodium ion and chloride ion, because they're aqueous here and they're aqueous over here. I didn't write the total ionics so that would be easy to see, but do it yourself if you'd like. Balanced formula, net ionic equation for the reaction. Okay, solubility rules, I get it. Is it potassium nitrate? Is it the red from this one and the blue from this one, or the silver, kind of a khaki color, to the purple? And the solubility rules say most iodides do dissolve in the water and all nitrates do dissolve in the water. I said most iodides except for silver, lead, and mercury iodide don't. So I think I'm going to write an equation about silver ion. Don't look, I'm going too fast, sorry. Silver ion colliding with the iodide ion. It's a +1 -1 combo. And so there's the total molecular equation, formula equation, some texts call it, and the net ionic equation. And give an example of how each of the following insoluble ionic compounds could be produced using a precipitation reaction. Write the balanced formula equation for each. How am I going to make iron sulfide solid? Well, how about if I took some iron 3 plus ion and poured together with some strong base sodium hydroxide water? What if I took some magnesium nitrate? All nitrates dissolve in the water, so I'd have I said magnesium, mercury, oh lord. Alright, MgHg, what's the difference? I'm kidding, I know the difference. Yeah. So, take some mercury 1 ion, mix it with some chloride, salt water, and I see a precipitation of mercury chloride. And likewise, solubility rules, most sulfates do dissolve in the water, but lead sulfate doesn't, and that's what forces this reaction, the lead sulfate. The sodium and the acetate are spectators. Most chromates don't dissolve in the water. That's kind of one of the unusual solubility rules. I don't know about part D here. Barium chromate would precipitate out. I don't like that last one. Whatever. Right, net ionic equations for the reactions of affinity that occur. Alright, are we tired of this yet? Or do you know your solubility rules? The first one, I think, chromium and hydroxide. Would the first of the first like to meet the second of the second? Is that a driving force for something to precipitate? In this case, yes. Or would the second of the first, the second of the first and the first of the second like to come together. In part A, no, sodium chloride dissolves in water. In part B, silver and carbonate. Yeah, that's it. Most carbonates don't dissolve in the water. The reason this carbonate got in the water in the first place is the ammonium ion. All ammonium salts are soluble. Mercury comes to what? That is a boo-boo. Oh, no, it's not. I had myself. I thought copper is hard to get dissolved in water, and so I was going to come copper nitrate, undissolves itself, precipitates. But not all nitrates dissolve in the water, so I got tripped up. Mercury sulfate. That's that weird dimercurous ion, and it's a 2 plus, and it's a sulfate, and mercury sulfate doesn't dissolve, which is weird for most sulfates do. Strontium and iodide, all iodides dissolve, all first semisalts dissolve. Nitrate, potassium nitrate, all potassium salts dissolve, all nitrate salts dissolve. So indeed, there's no impetus to do anything. Let's see what's next. Oh Lord, this is taking forever. You guys have some patience. Student wants to prepare a 1 liter of 1 molar solution of NaOH. If solid NaOH is available, how would the student prepare the solution? If 2 molar NaOH is available, how would you prepare the 1 liter of 1 molar? To help ensure 3 significant figures, to how many sig figs should the volume be, and volumes and masses be determined? Good enough question. If I want 1 liter of 1 molar, I'll take, that's 1 molar, that's 1 mole per liter, so I'll take 1 mole. That's 1 sodium, 1 oxygen, 1 sulfur, 40 grams, 40.0 grams, and that's 3 sig figs to 1.00 liters. If I'm diluting a more concentrated solution, M1V1 equals M2V2, and I want 1 liter of 1 molar, and I have 2 molar, so I take 500 milliliters, decimal milliliters of 2 molar, and water it down to 1.00 liters. Interesting. 1 mole of lead, solid lead nitrates added to 2 moles of aqueous potassium iodide, yellow precipitate forms. That's a lot of lead. Nasty for the environment. After the precipitate settles to the bottom, does the above solution conduct electricity? That's interesting. Lead nitrate and potassium iodide. Well, I need an equation for this. So here's the why in the world did I write that? Oh, I did. Lead nitrate dissolves in water, but it said solid. 1 mole of solid lead nitrate is added to 2 moles of aqueous potassium hydroxide. 2 moles of aqueous. Didn't tell me what the volume was, doesn't matter. And it is a 1:2 ratio, yeah. 1 lead ion to 2 iodide ions precipitates out. So this solid would precipitate the bottom, and eventually the top part would clear up. But the point is, these spectators are still left floating in the water, and that's plenty of ions to indeed conduct electricity and function as an electrolyte. Which of the following must be known to calculate the molarity? We haven't talked about molality yet. We've taken Gen Chem 2, we will in the first little bit of Gen Chem 2, but molarity is simply the mass or moles and what salt you have, mass or moles, and the total volume of solution. The volume of the water added is actually not mentioned. We could figure it out if we had a description of density, but not really on this one. Interesting. Think about it. Molarity. Calculate the molarity of the salt solution. Yep, that's right. Interesting. One more question. Differentiate between what happens when the following are added to water. Polar solute versus nonpolar solute. Well, if I add a polar solute to water, water's polar. So polar stuff dissolves other polar stuff. So this one gets dissolved in the water. This one probably just floats on top of the water. It might mix into little bubbles or micelles or little units, but if you shake it or stir it, but if you let it set long enough, most nonpolar solutes are liquid organic substances with the density less than 1, and oftentimes they float on water. Not always, sometimes they sink, but I'm just saying they would not mix. So speaking of polar solutes, the extreme case of the polar solute is the ionic solute, potassium fluoride, and this is just sugar. Oh, tricky. Whoa, you guys are mean. If I didn't know any better, I might guess C6H12O6 would not dissolve in water. And indeed, there might be a molecule that's not polar, and that with the formula C6H12O6, and it therefore wouldn't dissolve in water. But this one breaks up into ions, potassium and fluoride ions. This stuff, the molecule doesn't break up, but the crystals do dissolve. So this would be an electrolyte. This would not be an electrolyte. Whether or not it's sugar or whether or not it dissolves, this would not conduct electricity. But even if it was sugar, it would dissolve, of course, because that's not table sugar, but it's a simpler sugar. It would still dissolve in water if it was sugar, but would not conduct electricity. Non-electrolyte. Yeah, voila. Man, you guys made it through a long video. You deserve a break. Go do something relaxing or invigorating watching this stupid video. See you soon.